Okay, today in this class, that is the optical diffraction the fourth class, I'm going to discuss about the Fresnel integration, which is a very essential portion of a diffraction pattern of near region. So before start with the Fresnel integration, let us consider the approximation that are assumed by Fresnel during its calculation. The approximation I have already discussed, that the diffraction phenomena is basically the interference of different number of secondary wavelets that are produced by each and every point of the obstacle, and the wave can be divided, that wavefront which is generated as secondary wavelet, that can be divided into large number of strips. Those are called the Fresnel region, and we have to calculate the approximate sum of all those effect as the resultant effect at an external point. And obviously that effect depend on the distance and obviously the inclination factor. And as a recapitulation, so we already learned about that the resultant of an amplitude of any external point P is the sum of amplitude of all secondary disturbance, and the disturbance are coming from different zones. They are successively opposite phase to each other because all the zones are divided into the half of the period. Okay, and to get the maximum effect, we are going to construct the Fresnel zone by making external point alternately block. That means we making the alternate blackening of the regions of alternate zones. Now in this class I am going to discuss about the Fresnel diffraction integral. So before start with the integral, let us consider that there exists a opaque region. Firstly the rays are coming and these rays are illuminating this opaque region. তাহলে এই যে opaque regionটা আমি দেখতে পাচ্ছি, that may be rectangular aperture, that may be circular aperture, that may be a linear aperture, that may be anything. So firstly I have considered the general aperture through which the lights are coming or lights are entering into the region. And obviously in this aperture is on the alpha beta plane. So this aperture is lying on alpha beta plane. So these are the origin O, this is the origin, and any general point Q that has a coordinate alpha beta, and obviously this direction is Z direction, which is a common direction. And on this screen, on this aperture, sorry, no, not that screen, on this aperture plane, Z will be 0, right? So the position of Q point will be alpha beta, some alpha beta. And firstly, when any wave that are coming from a point source, the point source can emit spherical wavefront, and when those spherical wavefront are propagating towards the obstacle or the aperture region, and it get obstructed by the external portion of the aperture, except the region through which the wave is passing, the effect of the wave or amplitude of the wave that are entering except the region of aperture will be 0. Considering this fact, I have to take a function if alpha beta, that function is lying on this plane, and assuming this function, the value of this function if alpha beta equals to 1, when I consider the point is situated within that aperture particularly. And on the other hand, the value of this f alpha beta outside the aperture will be 0. Okay, so it's a very good approximation that taking a function if I am going to cut the effect of that incident wave, and I am going to limit the effect of incident wave within the aperture region. Okay, so outside the aperture region, the effect will be automatically 0. Now, those light rays are passing through this aperture and it is moving towards the point P. A screen is kept at this xy plane and P is any external point on which I am going to calculate the total effect of this diffraction due to this aperture. Now, to calculate the effect at P, I have to take the sum of effect of all the point which this aperture consists of. That means I have to consider that all the points that are lying within this aperture are responsible to generate the effect at a diffraction effect at point P. Okay, that is a good approximation. Now, if the spherical wavefront are entering into, all the points are going to generate spherical wavefront from this aperture. So the spherical wavefront that are obstructed by the point Q automatically generate secondary spherical wavelet. When the plane wavefront are coming and it is incident in the aperture, if the dimension of the aperture will be small, then it is going to generate the spherical wavefront again. Okay, and we are going to calculate the effect of all those secondary wavelets which are basically coming from that aperture or the point of the aperture at the external point P. Right now, P is situated at the point XYZ, and I keep the screen on the XY plane basically, which is approximately parallel to alpha and beta. So the point P will be XYZ. Now, what are the effect of all those secondary wavelet at any external point P? I have to calculate that. Now, to calculate that particular effect, we have to use our so-called Wiggins Principle. And Wiggins Principle automatically informs us about the nature of the points of any obstacle or the opaque region that can generate the secondary wavelet. If the incident wave is spherical, then spherical secondary wavelet can be a good approximation. So at P, the sum of the secondary wavelength that are coming from different part of the aperture must have different phases. Okay, now the transmission function which I have chosen, if alpha beta in the alpha beta plane, must have the form alpha beta equal to 1 inside the aperture and 0 elsewhere, right? So I have to take the effect of the point source. If S is the point source, then it will emit the spherical wavefront, and these are the spherical wavefront in the equatorial cross-sectional area I have to shown. And now if this spherical wavefront are obstructed by this region, it will again generate the secondary spherical wavelet. Okay. On the other hand, these are the plane wavefront which are incident on this obstacle, and if this obstacle are obviously of the smaller dimension, that dimension of lambda comparable to dimension of lambda, then it will generate the secondary wavelength, and that secondary wavelength are basically spherical and they are propagating along this direction, right? Okay, now see the effect of the plane wavefront, how the plane wavefront are obstructed by these two regions. In the Young-Sindel experiment, you can obviously see when you are going to calculate the effect of interference at an external point P. You can see the all this way, all these regions, they are going to generate the secondary wavelets at spherical 1 when the plane wavefront are incident on it. Now consider the three-dimensional wave equation, and how can I use the spherical wavelets as the mathematical expression of spherical wavelets. Any general form of wave that are basically generated in a region, that must be governed by this equation, that is del square psi equals to 1 by v square del square psi by del t square. You have already learned this. Psi is a wave function and v is the velocity of that particular wave through that region. Now as the waves spherical, basically the radius that are basically going to change, and the wave function psi, which must be independent of theta and phi, as the wave function has got spherical symmetry. তাহলে spherical symmetry থাকার জন্য wave ফাংশনটা theta এবং phi এর independent হবে. So del square, which is a spherical del square operator, that must have the form 1 by r square del by del r into r square del by del r into, as there is psi, so this is psi. So 1 by v square del square psi by del t square. Now to reduce this equation in the form of the soluble form, we have to consider that psi equals to 1 by r u r t. So u is a function of r and t obviously at the same time. So putting this psi equal to 1 by r u r t, this del squared u by del, this equation becomes del squared u by del r square 1 by v square del square u by del t square. You can simply put this equation in here and you just eliminate those terms and you can get this result. And the solution of this differential equation, that is del square u by del r square equals to 1 by v square del square u by del t square, the solution of this differential equation I can easily solve, because this is this equation have a reducible form by separation of variable. Okay, and we get the form as u1 equal to a1 f1 r minus vt and a2 equal to f2 r plus vt. These two waves are basically forward direction propagating wave and the backward direction propagating wave. So the harmonic solution of this wave and this function f must have the form of exponential e to the power I k r minus omega t. So the form of this equation, spherical harmonic wave a by r e to the power I k dot r minus omega t divided by r. So I can consider that when the waves are incident on this aperture and they are going to generate the spherical wavefront, this spherical wavefront must have a form a e to the power I k dot r divided by small r. Okay, so that will be a good approximation of a spherical wave. Okay, now consider the incident wavefront have the form e to the power I k r by r as is a spherical wave. Now the amount of that spherical wave that are basically transmitted through the region or the transmitted through the aperture must be f alpha beta with the transmittance function into e to the power I k r by smaller. So the quantity that are basically propagating through the aperture must be proportional to this function. So f alpha beta into the power I k r divided by r. Now r is the distance between the secondary wavelet source and the point of observation. How can you consider this r? Now consider that this Q point is going to generate a secondary wavelet of spherical. Okay, and that particular secondary wavelet that are generated by the point Q is basically going to the point P to generate the cumulative effect of diffraction. So when this, so at that particular situation, R is the simple distance between P and Q. Okay, so I consider R as the distance between secondary wavelet source and the point of observation. Okay, so the total effect due to all the secondary wavelets at the point P in the aperture, that is basically proportional to integration minus infinity to plus infinity. This is the transmission function of alpha beta e to the power I k r divided by r into obviously the area of that particular aperture d alpha into d beta. If you integrate all this term, you can get the effect of this diffraction at that external point P due to all the point sources present in the aperture. Now the total effect at point P is calculated as capital F XYZ. Okay, these are the total effect at point P due to diffraction. So this total effect will be equal to some constant into integration minus infinity to plus infinity f of alpha beta e to the power I k r by r d alpha into d beta. So f is considered as the effect of that diffraction at point P. So that f is basically the cumulative effect. Okay, now what is C? That's a big question. C is the normalized constant we have to derive out. Now how can we derive out the value of the C from this approximation? Firstly, when we are assuming that you are going to illuminate the aperture by a plane wave. If the aperture is absent, let us consider that there is no aperture, only the plane waves are moving from that point Q to the P. So the plane wave remain as plane wave if there is no obstruction. Now if the aperture is there, and you will have a spherical wavelet at P. Now if P is situated at a distant away from the aperture, the portion of the portion of the wavelets that are going to be for the calculation of your diffraction can be approximately assumed as plane wave. So any type of wave that are coming from the aperture region to the point P, that must be considered as a plane wave for a good approximation. Okay, so assuming this fact, I can say that this integration or the normalization condition is C integration if alpha beta will be 1, because we are considering only the regions within that aperture, and I left out the integration limit, that is minus infinity to plus infinity, because when you put f alpha beta value or the f alpha beta function and multiply it with the spherical wave, then it is automatically says that uh, there is no need to put the integration from minus infinity to plus infinity, because the region outside the aperture effect of the diffraction will be 0 according to the form of that f alpha beta, right? So C integration 1 into e to the power I k r divided by r d alpha d beta, the effect of all these things at any point P can be considered just a plane wavefront that are propagating to a distance z along z direction. So that wave is propagating along z direction. So this integration will be, for a good approximation, I can consider as this is equal to e to the power I k z. Okay. Now r is the distance between P and Q. So r in this case will be root over x minus alpha square plus y minus beta square plus z square. Okay. Now this, the value of x minus alpha and value of y minus alpha, that depends on the distance or the numerical aperture of this, and obviously the dimension of the screen. Okay, so if the aperture is comparable to the dimension of the screen, then the x minus alpha square and y minus beta square, both the term will be very less than z. And in the practical situation, when we are considering the effect of a diffraction, or we are considering to calculate some diffraction phenomena, automatically the value of those x minus alpha, that modulus, will be much less than modulus of z, and y minus beta, its modulus must be greater than, much greater than modulus of z. So automatically the value of those two becomes very less than z. So in that case, I can consider the binomial expansion of this term, and this equation becomes z, I put this z out of the square root, so z 1 plus alpha x minus alpha by z square plus y minus beta by z square to the power half. So definitely due to the diffraction phenomena, I can consider that
modulus x minus alpha very less than z, and modulus y minus beta that will be very less than z. And we can apply the binomial theorem, and as x minus alpha by z is very less than 1, I can remove or I can neglect the higher terms of x minus alpha by z and y minus beta by z. So the form of this equation will be z into 1 plus half of x minus alpha by z square plus half of y minus beta by z square. So from this equation, if you just take this z outside, so z will come out at z square here, and multiply this z with z square. So the term will be z plus 1 by twice z x minus alpha whole square plus 1 by twice z y minus beta whole square. Okay, now you are going to put the value of this whole thing in e to the power I k r. Now the value of e to the power I k r will be e to the power I k into this term, as r have the value this when x minus alpha and y minus beta is much less than z. And the value of e to the power I k r will be 1 by r e to the power I k z plus 1 by twice z x minus alpha square plus 1 by twice z y minus beta square. Right? Now as z is large compared to x minus alpha and y minus beta, the inclination of the r, line r, inclination of this line r with the horizontal will be much less than, much smaller. Now if the angle theta of inclination of PQ with the horizontal will be becomes small, then for a good approximation I can assume that r will be approximately equal to z, and z is the distance between this origin to this origin. Okay, this distance is basically z. So as this distance is z, so I can consider that r is basically approximately equals to z. Now the value of e to the power I k r by r will be 1 by z e to the power I k within the bracket z plus 1 by z x minus alpha square plus 1 by twice z y minus beta square. Okay, and put e to the power ikz outside, so it will be e to the power ikz by z e to the power ik by twice z x minus alpha square e to the power ik by twice z y minus beta square. Now this whole term have three portions. One is e to the power ikz by z, that is a spherical wave of radius z considered at distance z, and there are other two terms which are e to the power ik by twice z x minus alpha square and e to the power ik by twice z y minus beta square. Now these two terms, or the effect of these two terms, will be some numerical number, as there is some integrating factor. So the spherical wavefront from this line, you can say that as you are taking an incident wave as a spherical one, and at z point you are getting a wavefront of spherical, right? Okay, now the value of this integration, see the value of f alpha beta equal to 1 e to the power ikr by r d alpha into d beta equals to e to the power ikz. That is the approximation taken at the initial stage to calculate c. Now this will be c e to the power ikz by z and e to the power ik by twice z x minus alpha square into d alpha into integration e to the power ik by twice z y minus beta square d beta, that will be equal to e to the power ikz. Now this, consider this equation, this part of integration as I1 and this part of integration as I2. So c to the power ikz by z, I1 into I2 is the result. Now consider the form of that particular equation like the previous one, like this one. What is that? You can see the form of this equation in quantum mechanics in several times, that minus infinity to plus infinity to the power minus a theta square plus b theta into d theta, that will be root over pi by a e to the power minus e to the power into b square by 4a. Okay, now as you can see the form of this integration, you can generally calculate the values of I1 and I2. Now to calculate the value of I1, just I'm going to take out this integration form and substitute x minus alpha with capital gamma. Then minus d alpha will be d gamma, and I1 will be ik by twice z x minus alpha square into d alpha equals to minus e to the power ik by twice z gamma square into d gamma. And comparing this equation with this, I can get a equals to ik by twice z, and the form of this equation becomes e to the power ik by twice z gamma square into d gamma. So the value is minus of root over minus pi twice z by ik. This I2 have similar form if we consider y minus beta as capital theta square. So this will be minus d beta will be equal to d theta. So again we can get minus of root over minus pi twice z by ik. Okay, now when you get these things, you just put I1 and I2 in this equation, in the previous equation, that is in here, the value of I1, I2 and for IZ. You can get c to the power ikz by z minus 1 square root over 2 pi z by k whole square minus 1 by r, that will be ikz. Okay, and c will be minus I by root over twice pi by k whole square. So this will be minus I by lambda, k is equal to twice pi by lambda. So the value of I by lambda, so that will be 1 by I lambda. So as we get c equal to 1 by I lambda, I can say that the value of this fxy will be 1 by I alpha minus infinity plus infinity f alpha beta e to the power ikr by r d alpha into d beta. Now we get the effect at any point fxy. I eliminate the value of the another variable z, because I am going to consider the effect of f at on the plane xy. So just for simplification, I take the function as fxy instead of fxyz. So fxy will be 1 by I lambda z to the power ikz into this term. So the integration have two parts, f alpha beta to the power ikz into this square and f alpha beta to the power ikz into this square. So this equation is another form of Fresnel diffraction integral, and this equation represent the convolution between two function. One is this f alpha beta and other is the quadratic phase function, which is e to the power ik by twice pi x minus capital X square by minus beta square d alpha d beta. Now for the preliminary part, I am going to consider that I am taking a spherical wave, and the spherical wave are propagating through the region. But when you came to the form of that r, Okay, the form of this R, this becomes no longer a spherical. This will be the parabolic equation. So as this is the parabolic equation, if Z is very large, then we can replace the spherical wavefront by some parabolic wavefront for a good approximation. Okay, within this small region, so this sphere can be either shifted towards this direction or shifted towards this direction. So for a good approximation, I can assume this sphere as a parabolic one. Okay, there will be no problem at all. And just talking about the convolution function, if you consider that fx and gx are two functions of x, then convolution of f and g means the region of intersection f and g, the area of that portion only. And if we take g as a shifting function, that is x minus x prime, and taking the convolution of hx convolution x minus x prime dx, we are taking the common region of f and g. Okay, now take the rectangular function. This is a rectangular function fx, this is another rectangular function gx, and if you shift the gx at the right hand side between the limit minus b by 2 to plus b by 2, and if you shift it, now shift in such a way that you can get the effect of this convolution, that is the common region at this portion. Now this convolution function can be calculated in terms of Fourier transformation. Okay, that will be another portion. So up to that, I can end with the Fresnel diffraction integral. So these are the form of Fresnel diffraction integral. So thank you.